Today I want to talk about the propeller experiment. And I have a monograph on my website entitled Propellers, How They Work. And they're based in part upon my grandfather's aviation career, but also we get into the theory behind the propeller experiment. And so I wanted to leave that to give you the details of them on how propellers basically work and how to basically analyze them. But what I'm going to try to kind of cut to the chase in this presentation and work towards the experiment that we actually are planning on doing, which I'll show later in this video. But first, let's give a brief overview of the momentum theory. And there's a diagram in the propeller experiment. It looks like this, where it comes out and then it goes in. That's kind of exaggerated. But we have point 1, point 2 goes into the propeller, point 3 goes out, and point 4 leaves the control volume. And we have a velocity here, we have a velocity here, and a velocity here. And basically what we're going to do is we kind of consider the propeller, instead of going into all the complexities behind the blades and the way in which it acts as a screw through the air, we consider it just as a disc, because this is an axisymmetric solid around the propeller. And so this is, because obviously the tips of the propeller give you a circular trace, and so this is axisymmetric. So in any event, we're going to just consider this to be a disc, and this disc does something to the air. And what we do in most propeller theory and that you see in textbooks, and I actually replicate that in my monograph, it concerns V1 and V4 and the effect that the propeller has on the fact that the velocity increases from here to here, and the fact that this velocity is the average of the two. But we're going to do something a little different here. And something a little different is we are going to kind of skip over the rest of the control volume and just look at a 2 or 3. Basically, what we want to know to do is to consider the momentum theory as in this control volume, because what we're going to do is we're going to measure that using a pedostatic tube behind here, and we can start from here and go through in different positions. I'm going to go to that in just a minute as well. We're going to do all this. So, if you recall from solid mechanics, momentum, F delta T, and F can vary with time and whatnot, so let's just say Ft is equal to mass times velocity. In fluid mechanics, it actually is stated just slightly differently. Actually, m dot, which is V, or I can say this is that the change of mass to mass flow rate times the velocity. Now that's their basic theory behind that. The dm dt is equal to rho times q, or the volumetric flow through there. Basically, I take density times the volume, and then I can rho times area times the velocity, or rho area of velocity squared. And that is basically the momentum, that's how momentum is applied across this little control volume. Now, if I turn around and I measure the velocity on the backside of this as close as I can get to it, I have to be careful, because if I get too close, then I'm going to run into problems with turbulence and all this other stuff. So I have to kind of take a little balance here. And with that, and so I take these velocities, I get an average velocity, and I can say that this is the average velocity, and I can compute this, and I can compare it. If I've instrumented this thing, which is equal to thrust, I can compare it to an instrumented thrust, and I can get a result. That's the bottom line behind this experiment. Now, the tricky part is getting to this. And basically the problem is this. If I'm going to look at this one, look at this one. If I look at this propeller as a disc, and it's whirring fast enough so that the blades are going around and around and around, and I were to take, let's say, evenly with one, at least in the, let's see, one, two, across here, if I was to take evenly spaced, and I were to add it up, I would be wrong. Why would I be wrong? Because each of these points represents a different, we're going to say it covers a different area. The points on the outside of the circle actually are more meaningful to a larger part of this disk than the ones on the inside. So for example, the center one you take two halves this way, and then this, and then this, and then this. And each one of these points, this point represents the average velocity in this, and that velocity can be converted to a thrust by applying this equation, m times v squared for that area, rho, and I get F for the thrust for that area. And I do the same thing again, only this time I've got two of them. So I simply average those two, and I consider it for this area times that velocity squared times the rho again. Rho, we can pretty much assume that rho is close to the ambient rho we have. And we do that in the example I give in Chet's propellers. And I do the same thing for this, and this, and this. And you'll see, of course, is that these areas on the outside are larger than those on the inside. An alternate way of doing this would be to basically redistribute this where you have that all these are the same area. And basically the way you do that is you make these thinner on the outside and bigger on the inside. And you can have, and they do that with piping. Now, that is a good idea, but it's a little harder for someone to, unless you mark the traverse out properly, you're going to have problems with that. So we're going to do it this way. We're going to do it where we're going to weight basically these, and we add, in other words, this will automatically weight the effect of, say, this circle, this ring, and this ring, and this ring, and this ring, and this circle in the middle. And we're going to add all those up, and we're going to get a thrust, which by static equilibrium should be close to what it is here. And we'll get, we'll get all that, and we should be able to get that live happily ever after with this. So that, in a nutshell, is what we're going to be doing with this experiment. And I'm going to go to the lab now, and I'm going to show you how this actually works, and actually it works in the lab itself. By doing this, we can verify the momentum theory, and I state this very clearly, it's fairly crude. It works, and it's worked for a long time, because Froude came up with it in the 19th century, not with aircraft, but with ships. And so with that in mind, we're going to see how this actually plays out in data. So let's go to the lab and see how this works. This is our propeller experiment. We're actually in the lab, and this is the apparatus we're going to use. Let me give you a brief rundown of how this works and how we're going to use it. Over here, we have the computer which controls the apparatus, which is hooked up to it with a USB, and below it is the power supply. And the power supply furnishes the power to the system. Here in the middle, we have the actual test apparatus itself. When we run it, we're going to run it with this door open. However, this cage is designed for lab safety. It's designed to make sure that no one gets hurt when they're running this experiment. But we'll leave that door open just to make it easier for you to see on the video what's going on. And the test stand is inside, and it's hooked up to both the computer, which controls it, and the power supply, which furnishes power. And over here we have the traverse with the pedostatic tube right there, which basically, as we move it back and forth, I'm going to give you a little bit better view of that in just a second, we're going to be able to measure the velocity across the front of this propeller. Here we can get a little bit better view of the test stand, the propeller, which is behind the cage. But the main reason why I want you to look at this is to look at the traverse. The traverse basically moves the pedostatic tube back and forth across the front of the propeller. And the actual purpose behind that and how you break down the data from it is given in my description of the theory. Jet propellers, how do they work? And basically what we're going to do is we're going to start here at 12 centimeters from the center, because right here we set this thing up so that this pedos tube is right along the axis with the center of the propeller. And we have 12, and we're going to go in 2 centimeter increments: 12, 10, 8, 6, 4, 2, and then 0. And then we start with -2, -4, -6, -8, -10, and then -12. Now some of you are saying, well, shouldn't the minuses and the plus be backwards? Well, basically it doesn't make any difference which way, as long as we're consistent with the way we apply it. And we're going to move this traverse across, and we're going to take velocities after we start the apparatus. Let's go ahead and get started with the test. You will note that we have a little airspeed that it's recording. There's ambient conditions in the room that are contributing to that. And what I'm going to do is I'm going to start the apparatus. The traverse is set at 12 centimeters from center. I showed you what that was earlier. So let's go ahead and we're going to move in 2 centimeter increments across, just like I showed you. Now my objective is to get up to 5,000 RPM. Get up. Kind of easing it up, so we want it to overshoot. And of course, as the propeller speeds up, you get a little more airspeed, which you would expect. We'll just leave it there. That's close enough. Our goal is 5,000. This shows the apparatus running. We're at full speed right at the moment. On the left, you can see the propeller, the test stand. The test stand is fully instrumented to record the thrust that the apparatus is giving, the torque, power, and all that. On the right, you see the pedostatic tube coming out of the traverse. And the pedostatic tube will record the velocity. As I mentioned in the theory in jet propellers, how they work, our goal is to get as close as we can to the propeller to take the data without necessarily getting into a lot of the immediate turbulence and whatnot that surrounds the propeller. In other words, we're trying to have the best of both worlds. And we're going to see in this data collection how that comes out, but you can see how this runs. And then this time I've run it with the cage open so you can get a good idea of what it looks like. So with that, let's go ahead and run this test using the traverse from 12 centimeters over to minus 12 and take a series of velocities. And what we're going to do is we're going to actually, instead of recording this and then watching this, which is not very exciting and not very informative, we're going to actually record the screen output of the software which is used to record both what's going on with the test stand and what we're getting out of the pedostatic tube in the traverse. So let's go ahead and get that started. Now we've brought up the propeller to a speed of about 5,000 RPM. As you can see, as you would expect, the motor speed is a little jumpy, but it's pretty close. Speaking of that, if you look over on the left, before we start moving the traverse, I want to call your attention to a couple of things. One of them are the thrust, which is in newtons, and that's over, and that's also varying a little bit. That thrust should not change a great deal, actually theoretically not at all, if you have a constant RPM. And as you see, the RPM varies a little bit too, so you know we're dealing with something which is very close to being perfectly constant, but it's not. The second thing, of course, is the motor speed itself. We're going to go across the traverse from 12 to minus 12, and then we're going to up the speed and we're going to come back across the traverse. So right at the moment, we are taking data at a traverse position of 12 centimeters. Now I'm going to move it over to 10. And I'm going to let it stabilize a little bit. It's coming up a little bit. I'll let it stabilize. You also can read the airspeed jumping around on the left sidebar, but also there's that trace that you see towards the bottom center of the screen. Now we move the traverse to 8 centimeters. There we are, 8 centimeters. And you can see a definite pickup in speed from where we were at the start. Now we move it again to 6 centimeters. There we are. And it's doing quite nicely. If this were in the lab, you would probably have one person watching this or one or more watching the screen you're looking at and the other one moving the traverse. Now let's move the traverse over to 4 centimeters, and that's where it's at now. Now we move it to 2 centimeters. You notice that it's dropped off a little bit. You need to explain why that's so. And now we're at 0. When we set the device up, we aimed as you saw in the earlier part of the video, we aimed the pitot static tube directly at the center axis of the propeller. Now we go to -2. And now we move it over to -4. We move it over to -6. And we now move it to -8 is where it's at. And we go to -10. And last but not least, we go to -12. Now I have increased the propeller speed, to 6,000 RPM. You need to monitor, make sure that you know which readings are at which point. You also need to know, notice over on the left, make sure you've got your thrust recorded, because your thrust is going to be different. Obviously, that's kind of something that you would, I think we instinctively know, but to put the hard numbers to it is a good idea. But we're starting right now at -12. We're going to come back oppositely from the way we did it the first time. And now that you've recorded that, we're going to go down to -10. We're going to go down to -8. Now we see a significant uptick in airspeed. Now let's move the traverse over to -6. We move it again to -4. And we go now to -2. Again, you see the same drop towards the middle you saw before. You need to explain why that is so. And you get down to 0. There to +2. Here we are, we're at +2 now. And we move the traverse again to +4. We're at +4 now. +6. +8. I might mention that this propeller is an 8-inch diameter tip-to-tip propeller, and that may very well influence the way that you handle the calculations. Now we go to +10. And last but not least, +12. So now we've completed our data collection. You can use the same parameters, propeller size, etc., that you have in chest propellers, how they work. It's the same apparatus we collected, and the photos of it are also at that. So with that, it's been it's an interesting problem, propellers with momentum theory, and I hope you've enjoyed it. So thanks for watching, and God bless.